Hey everyone, today we're jumping into one of the most powerful tools in all of mathematics, matrices. Now, I know they can look kind of intimidating at first, but trust me, they're the key to simplifying some really complex problems, especially as you get into higher level calculus. So let's get started.
You've been there, right? Staring at a page full of x's, y's, and z's, trying to solve a huge system of equations. You're juggling substitutions, eliminations, and it just gets messy fast. It's so easy to make a small mistake. You've probably thought to yourself, there has to be a better way. Well, you're right, there is, and it's organized, it's elegant, and it's incredibly efficient.
So, here's our game plan. First, we'll talk about why we even need matrices. Then, we'll get into the core mechanics, how they actually work. After that, we'll uncover the real power with determinants and inverses. And finally, we'll put it all together and see it in action.
Okay, let's dive right in. This first part is all about making a shift, moving away from the chaos of doing these calculations by hand and into the clean, structured world that matrices give us.
So, what is a matrix, really? At its heart, it's just a grid of numbers. That's it. Think of it like a little container where we can neatly line up all the important numbers, the coefficients, from our equations. This simple act of getting organized is the first big step.
And that's really the big idea here. We're taking all the essential info from a problem and packing it into one compact grid. Why? Because it lets us handle the entire system of equations all at once, instead of messing with one little piece at a time. It's all about working smarter.
All right, so now we know why we use them. Let's figure out how to actually use them. This next part is all about the fundamental operations. These are the basic moves you're going to need in your toolkit.
Now, when it comes to multiplying matrices, there's one single golden rule you have to remember. It's row by column. Say it with me, row by column. You always multiply the rows of the first matrix by the columns of the second. If you can just burn that phrase into your brain, you've honestly mastered the hardest part. Let's see how it works.
Okay, let's walk through this one. To get that top number in our final answer, we take the first row, the 3 and the 1, and we multiply it by that first column, the -1 and the 2. So we get 3 times -1 plus 1 times 2. That gives us -3 plus 2, which is -1. Simple enough. Now for the bottom number, we just do the exact same thing with the second row. 2 times -1 plus 1 times 2. That gives us -2 plus 2, which is 0.
And boom, there's our result. A nice, simple column matrix with -1 and 0. See? We just combined two matrices into a new one, all by following that one simple row by column rule.
All right, next up we're diving into two of the absolute most powerful ideas in matrix algebra, determinants and inverses. Seriously, think of these as the keys to the kingdom. They're the tools that unlock what matrices can really do.
The determinant, it's just a single number that you calculate from a matrix. But this one number tells you a ton about your system. Before you do any other work, you can calculate this number and find out if your problem even has a unique solution. It's an incredible diagnostic tool.
And this is the most important rule of all. If you calculate the determinant and it turns out to be 0, that is a massive red flag. It means your matrix is what we call singular. It's just a fancy way of saying it doesn't have an inverse. And your system of equations doesn't have one single clean solution.
So, how do we find this magic number? Well, for a 2 by 2 matrix, it's super easy. You just multiply the diagonals and subtract. You just do AD minus BC. For bigger matrices, like a 3 by 3, it's a bit more involved. The method's called cofactor expansion, which basically just breaks the big matrix down into a bunch of little 2 by 2s to solve.
So I've mentioned this inverse a few times. What is it? The inverse, which we write as A with a little -1 superscript, is basically the matrix version of division. It's the one unique matrix that completely undoes the original. When you multiply a matrix by its own inverse, you get something called the identity matrix, which is just a matrix with 1s on the diagonal and 0s everywhere else. It's pretty much the matrix equivalent of the number 1.
Now here's the formula for a 2 by 2 inverse, and it's pretty cool. First thing you see is that 1 divided by determinant of A, right out front. See? That's exactly why the determinant can't be 0. You can't divide by 0. Then look inside the matrix itself. The A and D elements literally swap places, but the B and C elements, they just change their signs. You have to pay close attention to that. It is such a common place to make a little mistake.
Okay, that's enough theory. Let's see how all this stuff actually works in practice. We're going to walk through a few solid examples, step by step, just to make sure these ideas really stick.
Let's find the determinant of this 2 by 2 matrix here. Remember the formula, right? AD minus BC. So we just plug in our numbers. We get 2 times 3 minus 1 times 4. And that just simplifies down to 6 minus 4. And the answer is 2. Now here's the important part. Since the determinant is 2 and not 0, we know for a fact that this matrix is invertible. We know any system of equations it came from is going to have one single unique solution. That's what the 2 tells us. So up to this point, we've only been dealing with matrices that are full of plain old numbers. But, this is a calculus course. Things are supposed to change. So here's a thought. What happens if the numbers inside our matrix aren't just numbers? What if they're functions of a variable, like t? Can you actually do calculus on a whole matrix?
And the answer is a big yes. And you know what the best part is? It is so much easier than you think. You don't need some new, complicated rule. You just apply differentiation to every single element inside the matrix, one at a time, like they're all separate little problems.
Let's check out this example. To find the derivative of this whole matrix, we just pretend it's 4 tiny calculus problems we already know how to do. So the derivative of t cubed, that's 3t squared. The derivative of a constant, 6, easy, that's 0. The derivative of e to the negative t, that's negative e to the negative t. And finally, the derivative of 3t squared is just 6t.
And once we've done those 4 super simple derivatives, we just pop them back into a new matrix right where they started. And there you go. That's the derivative of the entire matrix. It really is that straightforward.
So let's do a quick recap of the big ideas. Number 1, matrices bring order to complicated systems. For multiplication, the rule to live by is row by column. Remember, the determinant is your key diagnostic tool. If it's 0, you've got a singular matrix. The inverse is just the undo button for a matrix. And finally, as we just saw, you can totally do calculus on matrices, and you just do it one element at a time.
We've covered a ton of ground, but now you are equipped with an incredibly powerful way of thinking about and solving problems. Not just in math class, but in physics, engineering, computer science, you name it. So I guess the only question left is, now that you have these tools in your back pocket, what complex systems are you going to go solve?